So the next talk by Ben Howard, who will speak on special cycles on moduli spaces of unitary Shtuka and higher derivatives of L functions. So please.
Okay, thank you. And especially thank you to the organizers for this opportunity to speak. So this should maybe, I mean, eventually I will get to derivatives of L functions, but that might not be until the very last lecture. So maybe this should really be called cycles on moduli spaces and higher derivatives of Eisenstein series. So as sort of a preamble, there's a long history of results connecting various special cycles on different things to coefficients of Eisenstein series. And the modern theory sort of starts with a paper of Herzebruck and Zagier in 1975, who just fixed a Hilbert modular surface and just working in the complex fiber, embedded lots of different quaternionic Shimura curves into it and started computing the intersection multiplicities of these divisors. And just by explicit calculation, they observed that these things happen to agree with the coefficients of Eisenstein series. And then Kudla and Milson sort of picked up on this idea and took it to its extreme and constructed analogous special cycles on much more general locally symmetric spaces, including lots of Shimura varieties. And they kind of explained in a more abstract way what was going on in the Herzebruck-Zagier theorem by showing that these cycles themselves, you should think of the cycles themselves as coefficients of modular forms, really as being like coefficients of theta series, geometric versions of coefficients of theta series. And then in particular, the Siegel-Wave formula relates theta series to Eisenstein series, and so you get some connection between these cycles on locally symmetric spaces and coefficients of Eisenstein series again. But these results are all on real or complex manifolds. And so then something important happened. The Gross-Zagier theorem came along, and Gross and Zagier did something formally very similar to what Herzebruck and Zagier did. They took a modular curve and then took its integral model to get something of dimension 2. And then on the integral model, they took Zariski closures of Heegner points in the generic fiber. And so now you have curves on a surface again, and they computed the intersections of these Zariski closures of Heegner points. And they showed that they matched up with Fourier coefficients of an Eisenstein series, except now it involved the central derivative of the Eisenstein series, or really a product of an Eisenstein series and a theta series. And this is really this calculation, this comparison of intersection numbers with coefficients of Eisenstein series is really the hard part in the proof of the Gross-Zagier theorem on heights of Heegner points. Because once you've connected the arithmetic geometry to an Eisenstein series, you just have to connect the Eisenstein series to the theory of L functions, and that comes through the Rankin-Selberg integral. So at this point, I want to make a shameless advertisement. So in August 2026, so along with Yanis Saklaridis, Jiwei Yun, and Wei Zhang, we're organizing a conference, the Gross-Zagier formula. "40 years later." So that'll be at MIT next summer. So please come, you're all invited. Okay. So then sort of after Gross and Zagier, Kudla and then Kudla-Rappaport started sort of combining the ideas that are in Kudla-Milson and in Gross-Zagier, and sort of said, well, what if we took some of these special cycles that are in the work of Kudla and Milson, take a nice case where these are actually cycles on a Shimura variety, where we have a nice theory of integral models for them. And so then we could try to do intersection theory on this integral model and try and get central derivatives of an Eisenstein series in the same way that Gross-Zagier did. And so they did this. They started out working on some low-dimensional orthogonal Shimura varieties, but the geometry of orthogonal Shimura varieties is very complicated because their connections with moduli spaces of abelian varieties are sort of rare and accidental and only happen in low dimensions. So then they switched to unitary Shimura varieties, which was in some sense much more productive. And they formulated a precise result, which I'll get to soon enough, saying that the degrees of certain zero cycles on these integral models actually matched up with central derivatives of a Siegel-Eisenstein series on, if you're on an orthogonal Shimura variety, you get an Eisenstein series on a symplectic group. If you're on a unitary Shimura variety, you get an Eisenstein series on a unitary group. So they conjectured this relation that they call the arithmetic Siegel-Weyl formula, and were able to prove it in some simple cases. And then the general case was proved by Chow, Li, and Wei Zhang just a few years ago. And a few years before that, something kind of wild happened. So Jiwei Yun and Wei Zhang, they looked at the Gross-Zagier formula again, but in the function field setting. And there was already a Gross-Zagier theorem in the function field setting proved by Doug Ulmer, where he proved a Gross-Zagier theorem replacing the modular curve with a moduli space of Drinfeld modules. But Yun and Zhang did something different. They, instead of a Drinfeld modular curve, they worked with moduli spaces of Drinfeld Shtukas. And something really amazing happened was that they got formulas not just for the central derivative of an L function, but for all of the higher derivatives at the center of the functional equation. And I, possibly like you, was always one of these people who thought, why should I really care about the function field setting? It looks just like the number field setting, but less interesting. And this completely changed my mind. The fact that they could get all derivatives of the L function was something that I found really fascinating. And then Feng Yun and Zhang sort of combined these previous two things. So they said, what if we take the cycles that Kudla and Rappaport were looking at on unitary Shimura varieties, moved those over to the function field setting and looked at Shtuka versions of them, and then try to do what Yun and Zhang did. And so they formulated and proved a higher derivative version of the Kudla-Rappaport arithmetic Siegel-Weyl formula over function fields, where the unitary Shimura variety is replaced with some moduli space of unitary Shtukas. They constructed cycles in not all, but many codimensions on these moduli spaces of Shtukas. And in particular, they were able to construct zero cycles. And when they constructed zero cycles, they could compute their degrees. And they showed that these degrees happened to match up with the Fourier coefficients of the rth central derivative of an Eisenstein series, of a Siegel-Eisenstein series on a quasi-split unitary group over a function field. And this last thing is really what my series of lectures is about. This work of Feng Yun and Zhang and extensions of it and applications of it are the goal of these lectures. But the organizers have granted me 5 hours to speak, which they may come to regret. And I have no interest in hammering you with 5 hours of technical lemmas and details. So I want to give a lengthy introduction by way of motivation to this work of Kudla and Rappaport that inspired this work of Feng Yun and Zhang, so that when I eventually switch to the setting of moduli spaces of Shtukas, we'll have some idea of the context where the ideas came from. So that's it for this little preamble. So most, if not all, of this first talk is going to be back in the Shimura variety setting. And then after that, all of the remaining lectures, I'm going to switch to moduli spaces of unitary Shtukas and try and get some higher derivative versions of the arithmetic Ziegel-Weyl formula, and eventually, probably not until the last lecture, actually get something that looks kind of like a higher derivative Gross-Augier formula, but on some moduli spaces of unitary Shtukas in low rank unitary groups. Okay, so here we go. Let's do blue. Okay, so cycles on unitary Shimura varieties. So probably nothing that I say in this talk is going to be my own work or even very new. If you've heard Kudlow or Rappaport or Wei Zhang or Chow Li speak about this stuff, many of you have probably heard them speak about this stuff over the last few years. But for those who haven't, here's a review. So let's fix a quadratic imaginary field. E, and fix an embedding into the complex numbers. And let's take a Hermitian space. V over E of signature n minus 1, 1. You could really take any signature you wanted. The thing that's special about this signature is that when we attach a Shimura variety to this Hermitian space, we're going to get special cycles on it in all codimensions. And if you pick a different signature, you'll get gaps in the codimensions. And in particular, you won't be able to construct the zero cycles that we eventually want to compute the degrees of. So if I take my Hermitian space V and tensor it over Q with R, this is a Hermitian space over the complex numbers. And the signature condition says, of course, that it admits a decomposition, many decompositions. As a positive definite space of dimension n minus 1, and a line, a negative definite line. And so we can look at the complex manifold of all such decompositions. So let's call that D. D for domain. So all decompositions. And of course, if I tell you either the positive definite part or the negative definite part, you recover the other one by taking the orthogonal complement. So we can think of this as the space of negative definite lines in this complex vector space, VR, which then realizes it as an open subset of projective space. In particular, this D has dimension n minus 1. And in fact, it's isomorphic to the open unit ball in n minus 1 dimensions. Okay. And then from this D, we get a Shimura datum. In fact, this is already a confusing point. If you start with a Hermitian space of signature n minus 1, 1, there's actually several different Shimura data you can associate to it. This is actually kind of annoying. We get a Shimura datum, G, D, where G is the unitary group of V. With GR acting in the obvious way, it acts on projective space over VR, and it preserves the negative definite lines inside of that, acting in the obvious way. So this Shimura variety, in particular, G is really the unitary group and not the unitary similitude group. So I said that you can attach more than one Shimura datum to this Hermitian space. There's sort of one for the group GU and another one for the group U, and the inclusion of the unitary group into the unitary similitude group is not a morphism of Shimura data, awkwardly. And so the Shimura variety for GU, that's the one that has the moduli interpretation in terms of abelian varieties. And this one is the one that doesn't. So this doesn't quite have a moduli interpretation, but these two different Shimura data, they're actually dominated by a third Shimura datum that does have a more complicated moduli problem. And so you can kind of fudge things, and you can take problems on this Shimura variety for this Shimura datum, and sort of by pulling back to this thing that dominates the one that has a moduli problem, you can kind of pretend that this one has a moduli problem, even though it doesn't quite literally. So we'll pretend that this has all the properties that one would want from a nice moduli space of abelian varieties. Okay, so then we fix a compact open subgroup. And then we're off and running. We get a complex Shimura variety in the usual way. Which we decompose in the usual way of some disjoint union of quotients of D by discrete subgroups G. So gamma G mod D, where gamma G is the usual G of Q intersect G, K, G inverse. And the reflex field of this Shimura datum is the quadratic imaginary field we started with, except in the weird case of signature 1,1, where the reflex field is actually Q. But in any case, even in the weird case, we can base change the canonical model to our quadratic imaginary field. So let's just say with a canonical model over the quadratic imaginary field that we started with. Now, because our Hermitian domain it came by construction, this is the Borel embedding of our Hermitian symmetric domain, it came by construction as a subset of projective space. So it has a tautological line bundle on it, which at every point of D assigns the line that that point of D literally is. So the inclusion of D into projective space gives a tautological line bundle. D, which is equivariant for the action of the real points of the group G acting on it. And so by the theory of automorphic vector bundles, you can descend this thing to the complex Shimura variety, but then once you descend it to the complex Shimura variety, it actually has its own canonical model. So we'll call this with its own canonical model. That I'm going to call LK, a line bundle on the canonical model of our Shimura variety. Okay, so we've got a Shimura variety and we have a favorite line bundle on it. And now we want to construct, in addition, lots of special cycles on it. So let's start by constructing some special divisors on it. So if I fix, so any, let's start with an X in V, and assume that it has positive Hermitian norm. So that'll determine an analytic divisor on D that I'm going to call dx. Well, if D is just all the negative definite lines in my Hermitian space VR, I can look at this subset of all negative definite lines that happen to be perpendicular to the vector x that I fixed. So negative definite lines in VR perpendicular to x inside of D. In fact, this, well, okay. If we set gx equal to the stabilizer in G of the vector x, then gx comma dx is a new Shimura datum that looks exactly like the one that we started with. It's the Shimura datum for the Hermitian space. Take, let's call it Vx equals everything in V perpendicular to x, which now has signature n minus 2, 1. So in particular, this gx dx has its own Shimura variety, and because gx is sitting inside of G and dx is sitting inside of D, this new Shimura datum comes with a fixed embedding of Shimura data into the one that we started with. Okay, so we've got all these divisors on our Hermitian symmetric domain. We want to construct divisors on the Shimura variety. So we need to take linear combinations of them so that they descend to the quotient. So here's how you do that. So if I give you a rational number, positive rational number t, and some Schwartz function on the finite adelic points of the Hermitian space. So the unitary group of V obviously acts on this Schwartz space. The adelic points of the unitary group act on this Schwartz space. And so I can look at a Schwartz function that's fixed by the action of our compact open subgroup. And we can get a divisor by summing over all vectors in our Hermitian space of Hermitian norm, the t that we fixed. I'll take the analytic divisor associated to the vector x. That'll be an infinite sum because V is not positive definite, but I can sort of cut this off to get a finite sum by sticking in the Schwartz function, and I'll insert an element of the group. And then this will descend. So it's a locally finite divisor on D, but because I summed over all the vectors of a given norm, and because my Schwartz function was fixed by K, this will be invariant under the discrete subgroup gamma G for any G that I fix. And so you repeat this construction. So this gives a divisor on one connected component of the Shimura variety. You repeat this construction on every connected component, and we get a special divisor. Z, K, T, phi, which is actually defined over the reflex field. And it's defined over the reflex field. That was sort of the point of explaining that we had this other Shimura datum to it. It's defined over the reflex field because this particular linear combination of special divisors literally is some linear combination of embedded sub-Shimura varieties. And that's how you get that it's defined over the reflex field. Okay, so we've got this huge collection of special divisors on our unitary Shimura variety, and now we want them in all codimensions. So we want cycles. All codimensions. D all the way up to the dimension of the Shimura variety, which is n minus 1. And once you've done divisors, it's pretty easy to guess how you're going to get things of higher dimension, higher codimension. Instead of fixing one vector, let's fix a D tuple. Vectors. This gives an analytic cycle. that I'm going to call dx. And it's all the negative lines that are perpendicular to all the components of my tuple. In other words, just take the divisors associated to all of them and intersect them. So you intersect D divisors and you'd hope to get something of codimension D, but of course that might not actually be true. For example, this dx clearly only depends on the span of the components, and there may be some linear relations among them. And so what is the actual codimension of this? The actual codimension is the rank of the moment matrix or the gram matrix of my tuple. Codimension, the rank of what I'll call HXX, which is really the matrix of all the Hermitian inner products of all the components of my tuple. Some D by D Hermitian matrix with entries in E. So that gives me a cycle on D, and now you take linear combinations of these cycles to descend to the Shimura variety in exactly the same way that we did for divisors. So to get a cycle, MK, let's fix one moment matrix. And a Schwartz function now on D copies of the adelic points of V, still fixed by our compact open subgroup. And look at, we'll sum over all D tuples of that fixed moment matrix, take the corresponding special cycle, and again, weight it according to the Schwartz function. And then this is constructed so that it descends to whatever connected component is determined by this element G. Okay. So we get a cycle. Z, K, T, V on MK of codimension the rank of the matrix T. And in fact, you can see this is 0. So the cycle is 0 unless T is positive semi-definite. So it's only interesting for positive semi-definite matrices. Okay, but we don't want a cycle in codimension rank T. We want a cycle in codimension D. And that's where this special line bundle, this tautological bundle comes in. So the yoga is whenever you see a special cycle that doesn't have the codimension that you want, you just intersect it in the Chow group with enough copies of this tautological bundle to shift it into the right codimension. So to get codimension D, define sort of a corrected cycle class. So when I put brackets, it means I've left the world of actual physical cycles and I'm working in the Chow group. And so this bracket Z is going to mean I take the naive cycle, which may have the wrong codimension, and then I just intersect it with enough copies of the inverse of the tautological bundle to end up in the right codimension, where the right number of copies is D minus the rank of the matrix. Okay. And then you can form the formal generating series. I'm going to sum over all D by D Hermitian matrices. Only take the positive semi-definite ones, take this cycle class, and make it the coefficient of some formal power series in Q. Now, the idea here, Nilsson, is that this is supposed to look like a theta series. So here's a theorem, presumably due to Siegel, very old school. If we had done this not on a Shimura variety, but back on a simpler positive definite Hermitian space, over our quadratic imaginary field, then for any d between 1 and n, which is still the dimension of V, and a Schwartz function on d copies of V, we can form the classical theta series. Theta, tau, phi. So this is supposed to look like this analytic cycle that we constructed. So I'll sum over all Hermitian matrices. And then take a power series in Q to the T, whose coefficients are, again, you sum over all the D tuples of vectors of a fixed moment matrix T. And you count them, except that if we fixed a lattice in V, we would just count the lattice tuples of lattice vectors of a given moment matrix. But instead of taking a lattice, we can just put in an arbitrary Schwartz function. And then this is a weight n Hermitian modular form, meaning on the Hermitian half space. Genus D. So this is you can realize this inside of D by D complex matrices here. So tau is some element in the Hermitian half space. Q to the T means e to the 2 pi I trace of tau times T, which makes sense because tau and T are both D by D matrices. And this Hermitian half space, so for the action of the quasi-split unitary group, where some gamma equals A, B, C, D in UDD acts by gamma tau equals A tau plus B times C tau plus D inverse, just like a Siegel modular form. And so I'm writing this in classical language because it makes the Q expansion the easiest to understand. But of course, really, this is just saying that the theta series is an automorphic form on this quasi-split unitary group. Okay, and so back to our Shimura variety, the motivation for forming this generating series is the following conjecture. So Kudla's modularity conjecture. So for all codimensions, this formal generating series and for any fixed Schwartz function, this formal generating series is a Hermitian modular form. Of the same weight n as in the classical case and on the Hermitian half space of genus D. So what does this mean for it to be a Hermitian modular form? What it means is that IE becomes one if you apply any linear functional coefficient by coefficient to the generating series. Which in particular, if this is true, implies that the coefficients actually span a finite dimensional subspace of the Chow group. Now, this conjecture, it's really frustrating that we don't know this. We should know this. So if you look at special divisors, so the case D equals 1, this follows from a result of Borchard's. So Borchard's never looked at, as far as I know, never looked at unitary Shimura varieties. He proved the analogous modularity result for orthogonal Shimura varieties. But this unitary Shimura variety always embeds into an orthogonal Shimura variety. And in the case of divisors, you can deduce the modularity on the unitary guy from the modularity on the orthogonal guy. And when D equals 1, this Hermitian half space, it's just the usual complex upper half plane. And the statement that this is a Hermitian modular form of genus D is actually the same as saying that this is just a classical modular form for SL2Z, for some congruent subgroup. Borchard's called his paper where he proved this result on orthogonal Shimura varieties, got a higher dimensional Gross-Kohn-Inzaghier theorem. Gross-Kohn-Inzaghier proved the modularity of a similar series of divisors, but where MK is replaced by a modular curve, and the Fourier coefficients are just Heegner divisors. Brunier and Raum they proved the analog. So Borchard's just worked with divisors. They proved the analogous theorem on orthogonal Shimura varieties in all codimensions. And then, so you could ask, okay, maybe the same idea should work for unitary Shimura varieties. And it kind of does. So a student of Raum named Chow in 2021, he proved the conjecture when the quadratic imaginary field is Q adjoined the square root of minus D, where D is 1, 2, 3, 7, or 11. And that's it. Then the proof breaks. So what's special about these quadratic imaginary fields? They have class number 1, but they have class number 1 for a very particular reason, that their rings of integers are actually Euclidean domains. And the Euclidean domains for the obvious norm, the norm form on the quadratic imaginary field. That's why these 5 appear. And there was a student of Yifeng Liu this same year who claimed to have proved the modularity for all E, but then Jia quickly looked at this thesis and immediately found the mistake because it was the same technical issue that he couldn't overcome. So we know this conjecture in at least some cases. And before this, Kudla and Milson they proved this. But after applying the cycle class map to cohomology, take this formal generating series with coefficients in the Chow group, and instead view all of these cycles as cohomology classes in the complex fiber. Then they proved that it becomes a modular form. So given all of this, we sort of should know this modularity result, but we still quite don't. Okay. So that's the picture in the generic fiber. And now let's talk about integral models. So now arithmetic Ziegelwey. So first, let me remind you of the classical Ziegelwey theorem. So now go back to a positive definite. B over E of dimension n. Yes?
You said that Kudla-Milson conjecture is known after applying the cohomology.
Yes.
So there is some subtlety about the kernel of the Chow group. What is
Sorry?
So there is some subtlety in the conjecture when one is dealing with Chow groups which are not represented by cohomology. It is in the kernel. The mapping from the Chow group to cohomology is not isomorphism.
That's correct.
And
Yeah.
what does kernel look like? And what is this?
Oh, the kernel of the cycle class map, the homologically trivial part of the Chow group. I mean, this is quite mysterious. What this looks like is the subject of the Beilinson-Bloch conjecture. I mean, it has a, yeah, I mean, it can have a very big kernel. So proving modularity after you apply this map is much weaker than proving modularity in the Chow group. Yeah.
Kernel is infinite dimensional, meaning it is. What does the kernel look like?
It's very mysterious. It's an interesting thing. I mean, if you took if MK is a curve and you take D equals 1.
Simply connected objects, no? Is unitary.
Oh.
No, maybe I'm mistaken.
If you look at codimension 1, then if you look at D equals 1, you might be able to say something about the kernel. But for general D, no, I think.
Okay. Okay. So if it was codimension 1, then things might be better.
Yes, definitely. I mean, in codimension 1, it is known.
That D was codimension 1. Okay.
Yeah, yeah.
Thank you.
Yeah. Okay. All right. So let's go back to the theta series. But now, I mean, there was a theta series of every genus D up to n. Let's look at the theta series of genus n. For the sum over all now n by n Hermitian matrices. Okay, the same business. So on the Hermitian half space, so the Ziegelwey theorem. So there's a Ziegelwey theorem for any genus, not just the genus the same as the dimension, but the one that's special about taking the genus to be equal to the dimension is that so now G is going to be the unitary group of this positive definite V. The theta integral. So the Ziegel-Wave formula doesn't quite say that a theta series is equal to an Eisenstein series. It says that some linear combination of theta series agrees with the value of an Eisenstein series. So you can take the theta integral. Where I take the Schwartz function and I translate it by the group and then average. And this is the value at s equals 0 of an Eisenstein series. E tau s on the Hermitian half space. And s equals 0 is the center of the functional equation. So it's the central value. So what you'd like to do is somehow go back and say, well, okay, we have this analog of theta series, but now they're generating series valued in a Chow group. So maybe if we take again the genus to be the dimension of the Hermitian space, we can connect these cycles to Eisenstein series. But of course, when we formed the special cycles, we were only allowed to go up to the dimension of the Shimura variety. So we can't go up to d equals n. But you can if you look at an integral model of the Shimura variety. So now back to V of sig n minus 1, 1. And now to talk about integral models, let's make some very particular choices. So fix L inside of V, a lattice on which the Hermitian form, let's just say, I want the Hermitian form to take integral values and assume that L is maximal with respect to that property. And for the compact open subgroup, I'm going to take the stabilizer of the lattice. And for the Schwartz function, I'm always going to take the characteristic function of, well, the obvious Schwartz function determined by the lattice. Okay. So with these choices, one can construct one can find moduli interpretations of everything. So M, which is our canonical model, the tautological bundle, and all the special cycles. And use these to construct integral models. script m now over spec OE, which is going to be smooth away from some bad primes, the obvious ones, smooth away from prime divisors of the discriminant of the quadratic imaginary field and the discriminant of the lattice that we fixed, and special cycles. Which are defined by some moduli interpretation. So once you have the moduli interpretation in the generic fiber, you can just repeat it on the integral model, and you'll get special cycles now in codimensions all the way up to the dimension of the integral model, which is n. Now, here's a little lemma proposition that's in the paper of Kudla and Rappaport, where they introduced these special cycles. So let's fix. So we're interested now in the special zero cycles on the integral model. So we're going to take d equals n, and let's fix a d by d, sorry, an n by n Hermitian matrix. Positive definite. And let Vt be just e to the n with that Hermitian form, that positive definite Hermitian form. And define a set called diff tv. It's going to be the set of all primes such that primes p, such that when you tensor this Hermitian space determined by t with qp, you don't get the one that we fixed. So there's a finite set of odd cardinality. Somehow because exactly because all the places of Q at which they don't agree has to be a set of even cardinality. And we already know that they don't agree at the Archimedean place because one is positive definite and one has signature n minus 1, 1. So if you look at the finite primes, this has to have odd cardinality. So the statement is 1 if the cardinality of this diff set is greater than 1, then the special zero cycle is actually empty. But if it consists of a single prime, then this special zero cycle is supported in the mod P fiber of the integral model. So these things are very small. They're very concentrated in single characteristics. And so here was the conjecture. So this is arithmetic Ziegel-Wey. Well, it's no longer a conjecture. So conjecture of Kudla-Rappaport proved by Chow, Li, and Wei Zhang. So this is the arithmetic Ziegel-Wey theorem. Okay, so there's some Eisenstein series. So we'll call it E tau S. So this is on the genus N Hermitian half space. In other words, it's an Eisenstein series on the quasi-split unitary group UNN. With a functional equation. In S goes to minus S, that forces it to vanish. It's an incoherent Eisenstein series with the following property. So if I take any positive definite n by n Hermitian matrix such that, okay, so I know that the corresponding special cycle, if it's non-empty, is going to be concentrated in a single characteristic. I want to assume that that characteristic is a prime of good reduction for the Shimura variety. I want to avoid the ramification. So diff TV equals P, where P is not one of the bad primes. Let's see, so there's an Eisenstein series such that for all positive definite, we have, so we can take now this zero cycle that's supported in characteristic P, we can take its degree, and when you take the degree, you get the central derivative of the teeth coefficient of the Eisenstein series. And if you take a positive definite T, so it's that this diff set has more than one element, then we know that this zero cycle is empty. So the left-hand side is zero, and the right-hand side also turns out to be zero. Okay. So this is the arithmetic analog of the Siegel-Vey theorem. And just a remark, if P is one of the bad primes, if it divides the discriminant of E, or if it divides the discriminant of the lattice, there are versions of this. So for the discriminant of E, there are results of he, Li, she, and yang. And if P divides the discriminant of the lattice, there are similar results of Chow, he, and a different Zhang, Jiyu Zhang. So this is the result that we want to generalize to the function field setting, where this first derivative is going to be replaced by derivatives of whatever derivative you want, the rth order derivative for any r. Okay, so let's see, I'm supposed to stop at 5:30. Okay, I've got 15 minutes. So for 15 minutes, I can either talk about what happens when T is not positive definite, or I can tell you more about how you construct this integral model and the moduli interpretation of these cycles. Let's see. Let me tell you about the moduli interpretation. Maybe this is a good place to pause for questions before I do that. This is sort of what this series of lectures is about. Generalizing this.
Hello.
Yeah.
The previous slide, this Eisenstein series that you wish to have,
Yes.
Fourier coefficients are non-zero only on positive definite Hermitian matrices or on
No.
all?
It's not. This omission of T being positive definite is deliberate. Yeah.
It's not.
It's only a claim about the positive definite coefficients. So if you have non-positive definite coefficients, or even it can even have like negative definite coefficients. There are versions of this, conjectural versions of this, but they're more complicated. Maybe I'll do that instead of the moduli interpretation. Well, it's a little bit shorter. and 15 minutes is not a lot of time. So yeah, let me do that instead. So let's scrap this. Okay. Where's page? Page 14. There we go. What if t is not positive definite? Okay. Well, first of all, z of t has codimension. The naive cycle, defined by the moduli interpretation, its codimension is going to be too small. It's going to be the rank of the matrix T. You can still form this sort of corrected cycle class. So I'm lying a little bit. I mean, when you formulate the moduli interpretation and construct this naive cycle, it's not even equidimensional. It's much more complicated than what you see in the generic fiber. But I mean, there are sort of ways to get around this. But so we're just going to pretend that it has codimension rank T. You can, in fact, construct some cycle class that really has the correct codimension. But let's just ignore that point and pretend that it has codimension rank T. And then I said that this tautological line bundle still extends to the integral model. So you can still correct it in the obvious way. And you'll get a class in the codimension n Chow group of the integral model, the Chow group of zero cycles. But you've really lost something here, because when you intersect with this tautological bundle, you've really lost a physical cycle. You only have a cycle class in the Chow group. But the degree of a zero cycle on M is not constant on its rational equivalence class. So there is no degree. On the Chow group of zero cycles. You can talk about the degree of a physical zero cycle, but the degree of a zero cycle class is not a well-defined thing, even if the integral model is proper. So this is somehow the reason why we have Arakelov theory. The reason, you have to think about this. Why is the degree not defined? It somehow has to do with the fact that the divisors of constant functions are now kind of weird looking. If you were in the generic fiber and you look at a non-zero constant function, it doesn't vanish anywhere. But if you're on the integral model and you look at, say, the constant function p for some prime p, that function vanishes along the mod p fiber. And so this weird behavior of divisors of constant functions is somehow what accounts for this degree not being well defined. So what do you do? So the solution is to work with the arithmetic Chow groups. Chow hat D M of Gillet and Soulé. So this would be a pair consisting of, so it's the set of all Z, G, modulo some notion of rational equivalence, where Z is an actual codimension D cycle, and this G is a green current for the complex points of the cycle inside the complex points of the Shimura variety. So if you're looking at zero cycles and you have a zero cycle it's going to be supported just in characteristic P, its complex fiber is empty, so you can take G to be zero. So that's sort of implicitly what's going on in this arithmetic Ziegel-Weil theorem. This zero cycle is being upgraded to something in the arithmetic Chow group by just taking the zero green current at infinity. So you can endow any special cycle with a green current in a distinguished way. So this construction is due to Luis Garcia and Siddharth Sankaran. To get sort of naive arithmetic cycles in the Gillet-Soulet arithmetic Chow group. Let me, yeah. So this, it's now going to live in the codimension rank T arithmetic Chow group. And you can endow, in some natural way, this tautological line bundle with a metric in the complex fiber in some canonical way. And that'll give you some metrized line bundle in pick hat of M, the group of metrized line bundles, which is the same as Chow hat 1. And these arithmetic Chow groups of Gillet and Soulet are constructed so that there's still an intersection pairing on them. So we can define this sort of corrected arithmetic cycle class in the same way that we did before. Which now lives in the arithmetic Chow group of the correct codimension. So let's take T to be n by n so that we're getting arithmetic zero cycles. And once you augment these things to the arithmetic Chow group, then there's a notion of arithmetic degree. So then the general conjecture is that for all T, so this is n minus rank T, for all T, the arithmetic degree of this now augmented thing is equal to the central derivative of the Tth coefficient of the Eisenstein series. And this includes matrices T that are not positive semi-definite. And when it's not positive semi-definite, this naive cycle, Z of T, is just empty. But you can always, this construction of Garcia and Sankaran still produces an interesting green current for the empty cycle. And so this is an interesting equality, even if T is not even positive semi-definite. It's just somehow a purely Archimedean thing. This becomes just a statement about the green current and not about the arithmetic geometry at all. And so what's known about this general conjecture? So, I mean, it takes a lot more work even to formulate it, but in the case where the rank of T is n minus 1. So if you look back up here, that means we're taking exactly one copy of the tautological bundle here. So we would have an arithmetic cycle in dimension 1, and then this tautological bundle in codimension 1. You can intersect them and take the arithmetic degree of this. And this is proved so sort of hot off the presses. So this is in Ryan Chen's PhD thesis. And at the other extreme, you could ask, what happens if I just straight up take T equals 0? That's allowed. if t equals 0, then of course it's a matrix of rank 0. So this cycle becomes, well, it becomes the fundamental class of the Shimura variety, and you're just getting this arithmetic cycle really is just the n-fold intersection of a bunch of copies of the tautological bundle. It's just a statement about the tautological bundle. And in this case, this arithmetic Ziegel-Wey theorem, so I did this with Jan Vernier. So it's kind of funny. So Chow, Li, and Wei Zhang, they did the non-singular case where T is positive definite, it's a non-singular matrix. If you allow T to be slightly singular, the situation becomes much more complicated, but it's known. And then you can go to the absolute other extreme where T is completely singular. And it's known in that case too. And so you could hope that maybe you can keep working in, but so far that seems to be difficult. And this seems to be these cases, the non-singular case in Li and Zhang, this case, the almost non-singular case in Ryan Chen's thesis, and the extremely singular case are the only ones that are known at the moment. Okay, so that I believe is the end of my time. And so in the remaining lectures, we will never look at any of this stuff again. We're going to leave the world of Shimura varieties completely. In the next lecture, I'm going to explain what the analogs of these objects are in the function field setting. And then in the third lecture, I hope to sketch the proof of the analog of this arithmetic Ziegel-Wey theorem in the function field setting due to Feng, Yun, and Zhang. The new result that I'll eventually get to is an extension of that, which looks like this case. So the almost non-degenerate case. And then in the final lecture, you feel like once you've proved something like this arithmetic Ziegel-Wey formula, where'd it go? Yeah. You've somehow done the hard work. You've connected cycles to something in automorphic forms. And so can you push that a little further and actually relate this to derivatives of Langland's L functions? And you can, again, by finding situations where this Eisenstein series fits into some sort of Rankin-Selberg-like integral. So in this setup, the relevant thing is going to be the doubling integral of Piatetsky, Shapiro, and Rallis. And so lecture 2, extend this arithmetic Ziegel-Wey, explain the statement of arithmetic Ziegel-Wey in the function field setting. Lecture 3, try to explain some of the proof. And lecture 4 is try and give some applications of it where there are actual L functions involved. But that is all for today. So thank you.
Are there questions, comments?
Rigid analytic setting.
The rigid analytic setting.
This is vague, but I don't know.
I mean, I think of these results as being very sort of global things. I don't know an answer to that. I don't know what sort of p-adic analogs would be. I mean, there are the hard work in proving this arithmetic Ziegel-Wey theorem is in some sense a local thing. You can relate these. The first thing you do in proving it is replace the Shimura. So this cycle is supported in a single characteristic P. So if you want to prove this, the first thing you do to compute the left-hand side is replace the Shimura variety by a Rappaport-Zink space. But it's really the formal scheme, the integral Rappaport-Zink space, where this is happening. If you pass to the rigid analytic fiber, it's a really good question. So there is some work of Andreas Michał where he tries to formulate a theory of intersection theory that really works not on the integral model of the Rappaport zinc space, but only on the generic fiber. And so it's kind of a tantalizing idea to suggest that maybe one could try and reprove this formula without ever at all looking at integral Rappaport zinc spaces, only working with their rigid analytic fibers. But that's more of a dream at the moment, or wishful thinking. And it would be nice if one could do that, because it would help to solve a lot of the technical difficulties that come at primes of bad reduction, if you could just do everything in the generic fiber. But I mean, what Michał did is basically, I mean, all of these arithmetic Chow groups involving dowing things with green currents in order to make better sense of the notion of degree. So he works with a kind of rigid analytic notion of green current. But I guess that's my answer. There's some work of Michał that kind of maybe lays some of the theoretical foundation for how one might formulate this sort of thing in the rigid analytic fiber. But actually doing it is something that at the moment I think is wishful thinking.
Thank you.
More questions, comments? So if not, let's thank the speaker again.